A collection of capacitors in a circuit can be analysed as a single equivalent capacitor with some equivalent capacitance CEQ. Now if we consider capacitors connected in series, and we have a battery that's going to be used to charge these capacitors, then the voltage across both capacitors is equal to the sum of the individual voltages. And recall that capacitance is the charge stored on a capacitor on the voltage across the plates. And in this case, we have the electrons flowing from the battery, which gets stored on a negative plate of this capacitor, and these repel electrons from the top plate, leaving behind a net positive charge. And the repelled electrons build up on this plate, which repels electrons from the top plate, leaving behind a net positive charge on the top plate. So by the conservation of charge, each capacitor in series is going to have the same charge on their plates. So we have Q1 is equal to Q2. So from the capacitance, we can write the voltage as the charge on the capacitance. And therefore from this equation, we have the charge on the equivalent capacitance to these capacitors in series is equal to the charge on the capacitance of one capacitor plus the charge on the capacitance of the other capacitor. So note that the net charge on the equivalent capacitor is going to be Q. So we can cancel the charge, and therefore we have the reciprocal of the equivalent capacitance in series is equal to the sum over the number of capacitors that we have in series, and we're summing the reciprocal of the capacitance of each capacitor. So the equivalent capacitance of the capacitors in series is going to be less than the capacitance of the smallest capacitor. So as you can imagine, this plate is going to attract electrons from this plate, which will thereby reduce the capacitance of the individual capacitors. Now when we have a set of capacitors in parallel, then the charge is going to build up on both capacitors. So you'll get negative charge building up on the bottom of each of their plates, and these repel electrons from the top, which flow back to the cathode of the battery. So because these electrons are repelled, you get positive charge left behind on the top plates of both capacitors. So in this case, the voltage across both of those capacitors is equal because they're in parallel. And by the conservation of charge, you have the charge flowing from the battery onto those plates is the sum of the charge stored on the plates of capacitor 1 plus the charge stored on the plates of capacitor 2. And now using the formula for capacitance, we can write the charge as the capacitance by the voltage. So we have the equivalent capacitance of the group of capacitors in parallel multiplied by the voltage, which is constant across those capacitors, is equal to Q1, which is the capacitance of capacitor 1, by the voltage across it, plus the capacitance of capacitor 2 by the voltage across the capacitor. So as we said, the voltage is constant, so that's going to drop out, and therefore we have the equivalent capacitance of a set of capacitors in parallel is the sum over the number of capacitors, and we're summing the capacitance of each capacitor. So as you can imagine, in this case, the equivalent capacitor is going to have a higher capacitance than the individual capacitors. Because you can imagine adding the negative charge on both bottom plates and the positive charge on the top plates. So in this case, these capacitors don't nullify each other, like the capacitors in series, as we explained. So recall that these results are opposite to what we got for resistors. Let's look at resistor capacitor circuits. So here we have a battery connected to a resistor and a capacitor, and we initially have an open switch. So therefore there's no current flowing through this circuit, and the charge on the capacitor is 0. Now when this switch is closed, we're going to apply Kirchhoff's law. So that's the electromagnetic force of the battery minus the voltage drop across the resistor, which is the current, and that's a function of time, by the resistance, and minus the voltage across the capacitor. So therefore around the closed loop, the net voltage is 0 by Kirchhoff's loop rule. Now just as we close the switch, we have current flowing through the circuit, and the voltage across the capacitor at time 0 is initially 0. So therefore, the electromotive force minus the current at time 0 multiplied by the resistance is 0. And therefore the initial current in the circuit at time 0 is the electromotive force on the resistance. So the capacitor initially behaves like a wire. Now as charge begins to accumulate on the capacitor, the voltage across the capacitor opposes the EMF provided by the battery. So noting that the current is the instantaneous rate of change of charge with respect to time, and recalling the capacitance is the charge stored on the capacitor on the voltage across the plates, then we can write the voltage as a function of time as the charge, which is also a function of time, on the capacitance. So note that so far we've looked at circuits when the current in the circuit was constant. But now as we close the switch, the current is going to change with time until it reaches a steady state. So what we have is the electromotive force is equal to dq dt by R plus Q on C. So if we divide through by R and separate the variables, so basically we'll multiply this first term by the capacitance on the capacitance, So we can now write the differential equation as dq dt is equal to the capacitance by the electromagnetic force minus Q on RC. And now if we separate the variables, we get dq on C by epsilon minus Q is equal to 1 on RC dt. And now if we integrate both sides and apply U substitution for the integral on the left, we get U is C epsilon minus Q. So therefore du is minus dq. So what we get is minus the integral of du on u is equal to minus the natural log of u, where u is C by epsilon minus Q. And that's equal to 1 on RC by T plus a constant of integration. And now if we divide through by minus 1, we get a minus and a minus, and then take e to the power of both sides. So we get C by epsilon minus Q is equal to e to the negative 1 on RC by T, and that's multiplied by e to the minus C1. So that's the same as having e as the base and adding the indices. So this here is just another constant. So we end up with C by epsilon minus Q is another constant by e to the negative 1 on RC by T. So at time t equals 0, there's no charge on the capacitor. So what we get is C epsilon minus 0 is equal to C2 by e to the 0, which is 1. So let's replace C2 with C epsilon. And rearranging this equation for the charge, we have the charge as a function of time is equal to C epsilon by 1 minus e to the minus 1 on RC by T. And what we do is set tau to be equal to the resistance by the capacitance, and rewrite this expression as e to the negative t on tau. And this is the solution to the ODE that predicts the charge on the capacitor when it's charging. And we'll analyze this solution in more detail. Now that we've charged the capacitor, we had positive charge on the top plate and negative charge stored on the bottom plate. So we'll call this the initial charge Q0. And then we opened the switch and took out the battery. So recall that we had Kirchhoff's law applied to this loop was the electromagnetic force of the battery minus the current as a function of time by the resistance and minus the voltage across the capacitor was equal to 0. And now we no longer have this electromagnetic force. So when we close this switch, we have the initial voltage across the capacitor at time 0 being equal to V0 because the capacitor is already charged. So therefore the current at time 0 is equal to minus V0 on R, according to this equation. So as you can imagine, when this capacitor is going to get discharged, then using conventional current, we'll have the direction that positive charge would flow, going this way, from the positively charged plate towards the negatively charged plate. But we know that the electrons are the actual charge carriers, and this flow of charge is just used as a convention. So that's why our initial current is negative, because when we connected the battery, current was going anti-clockwise. But now that we disconnected the battery and the capacitor is discharging, the current's going to flow in the opposite direction. And dividing through by -1, we get positives on the left hand side, and the current is dq dt, and multiplied by the resistance plus the voltage across the capacitor. So recall the capacitance is the charge on the voltage. So the voltage across the capacitor at time t is equal to the charge at time t on the capacitance. So note that charge begins to leak off the capacitor when we close that switch, and the voltage drops over time. And so does the current. So now if we divide through by R and rearrange this equation for dq dt, so that will be equal to minus q on RC. And now if we separate the variables, we get dq on q is equal to minus 1 on RC dt. And then integrating both sides, we get the natural log of q is equal to minus 1 on RC by time t plus a constant of integration. And now if we take e to the power of both sides, we get q as a function of time is equal to e to the power of this term multiplied by e to the power of this term. So that's the same thing as e to the power of the sum of the exponents. So e to the power of c1 is just another constant, and that's multiplied by e to the minus 1 on RC by time. So in this case, our initial condition is the charge on a capacitor at time 0 is equal to the initial charge, Q0. So that gives Q0 is equal to C2 by e to the power of 0, which is 1. So therefore our constant of integration is equal to the initial charge stored on a capacitor. And again, we take this quantity, RC, as time tau. So therefore we can write this as e to the minus t on tau. And the significance of the time constant will become apparent when we analyze this solution. Let's analyze the solution first for the case of when the capacitor is charging. So recall when we closed the switch, the capacitor acted like a wire. So at time t equals 0, this term is 1, and therefore the initial charge on the capacitor is 0, and this increases until it asymptotes at this value C by epsilon. So recall the capacitance is the charge on the voltage across the capacitor. So therefore, when the charge asymptotes, we have C is equal to the final charge on the capacitor on the electromotive force. So therefore we can write this as the final charge on the capacitor. And we can see that the charge stored on the capacitor is proportional to the voltage. So therefore the voltage across the capacitor behaves the same way. Now if we differentiate this expression, we get the current. So that's equal to QF on tau, which is the resistance by the capacitance, by e to the minus t on tau. And according to this expression, QF on the capacitance is equal to the electromotive force provided by the battery. So therefore at t equals 0, the current in the circuit, when the capacitor is behaving like a wire, is epsilon on R, and this decreases exponentially until it reaches 0. So therefore the charge in the capacitor, the potential difference across the capacitor, and the current in the circuit vary in the following manner with respect to time, and they asymptotically approach steady state conditions. And also the electric potential energy stored in the capacitor is also going to asymptotically reach steady state conditions. So recall that was equal to 1/2 by the charge by the voltage across the plates. So we can see that after a long time, a charging capacitor approaches the state of being fully charged, reaching a maximum potential difference where there's 0 current in the circuit. And now for the case where the capacitor is discharging, so it's initially carrying some charge, so immediately after we close the switch, the amount of charge on the capacitor, being initially Q0, starts to decrease along with the energy stored in the capacitor. So the charge decreases exponentially as follows until it reaches 0, where the capacitor is completely discharged. And if we differentiate Q with respect to time, we get minus Q0 on tau, which is RC, by e to the minus t on tau. So as we said, Q on the capacitance is equal to the voltage. So this Q0 on C is the initial voltage across the plates of the capacitor. So therefore, the current starts from minus V0 on R and then asymptotes to 0. So recall when we had the battery, the conventional current was anti-clockwise, and when we don't have a battery, the conventional current goes in the opposite direction. So effectively, the amount of charge on the capacitor, the potential difference across the capacitor, and also the current in the circuit all decrease until a steady state is reached. Now the time constant tau is a significant quantity of an RC circuit. So it's a measure of how quickly the capacitor will charge or discharge. So noting that tau is equal to the resistance by the capacitance, so verify that this is in units of time. So for a charging capacitor, if we substitute T equals tau, we have Q of tau is equal to the final charge by 1 minus e to the negative 1. So that's approximately equal to 0.63 of the final charge. So the time constant tau represents the time required for the capacitor's charge to increase from 0 to approximately 63% of its asymptotic value. Now conversely, for a discharging capacitor, we have Q of tau is equal to Q naught by e to the minus 1, which is approximately 0.37 Q naught. So that's somewhere around here. So the time constant in this case represents the time required for the capacitor's charge to decrease from fully charged to approximately 37% of its initial value. So for both the cases of charging and discharging, for times that are much larger than the time constant, the capacitor and the circuit can be modeled using steady state conditions. Consider the following circuit where the switch is initially turned on at time t equals 0. And in part A, what is the time at which the total charge stored on both capacitors reaches a quarter of its final value? We'll recall that for capacitors in parallel, the equivalent capacitance is the sum of the capacitance of the individual capacitors. And when the switch is closed, the capacitor is going to start charging. So we use our solution to the differential equation for a charging capacitor, where we have Qf being the final charge on the equivalent capacitor, which is the total charge stored on both capacitors, and that's multiplied by 1 minus e to the minus t on the time constant tau. And recall that tau is the resistance R by the capacitance, and in this case that's the equivalent capacitance of our parallel capacitors. Now when the total charge reaches 1/4 of its value, we equate 0.25 by the final charge is equal to the final charge by 1 minus e to the minus t on tau. And now we cancel Qf, and 0.25 minus 1 is minus 0.75, by negative 1 is 0.75. So that's equal to e to the minus t on tau. And taking the natural log of both sides, we have the natural log of 0.75 is equal to minus t on tau, and then if we multiply through by tau, we get R by the equivalent capacitance. And dividing through by minus 1, we get the following expression for the time. So minus the natural log of 0.75 is 0.288. So the time at which a total charge stored on both capacitors reaches a quarter of its final value is 0.288 by the resistance by the equivalent capacitance. And in part B, what is the total electric potential energy stored in both capacitors when the current through the resistor is 0? So recall the electric potential energy in a capacitor is 1/2 by the charge stored on its plates by the voltage across the plates. So in this case, as the time approaches infinity, the current through the resistor approaches 0. So therefore we end up with the charge on the capacitor is QF. And when our equivalent capacitor is fully charged, the voltage across both of these capacitors is equal to the electromotive force supplied by the battery. And recalling that capacitance is the charge on the voltage, well, in this case we have the final charge on the equivalent capacitor, the voltage across the plates is equal to the EMF of the battery when the current through the circuit is 0, and the capacitance is equal to the equivalent capacitance. So therefore QF can be written as the equivalent capacitance by the electromotive force. And that's the energy stored in both capacitors. Now in part C, if the battery is removed after the capacitors are fully charged, then find the total energy dissipated by the resistor. So the power, being the rate at which energy is dissipated in a resistor, is equal to the current by the voltage at time t, which is equal to the current squared by the resistance. So here we applied Ohm's law because the resistor is an ohmic circuit element. And recall that the differential equation for a discharging capacitor had the following solution, which was the initial charge on the capacitor by e to the minus t on tau, being the time constant. So when the battery is removed after the capacitors are fully charged, then the total charge on our equivalent capacitor is equal to the equivalent capacitance by the electromotive force, in accordance with this expression. And now if we differentiate Q with respect to time, we get minus the equivalent capacitance by the electromotive force on the time constant, which is the resistance by the equivalent capacitance, and that's multiplied by e to the minus t on tau. So if we cancel CEQ, our expression for the current as a function of time is minus epsilon on R by e to the minus t on tau. And now if we square the current, we get epsilon squared on R squared by e to the minus 2t on tau. And then multiplied by the resistance, we get R in the denominator. So this is the rate at which energy is dissipated by the resistor. So if we want the total energy dissipated by the resistor. We want to integrate the power dissipated by the resistor. So taking the constants outside the integral, we're integrating e to the minus 2t on tau over time. And recall that when the time approaches infinity, the current approaches 0. So we're going to integrate from time 0 to infinity. And this is an improper integral, so we're going to evaluate it using dummy variables. So we'll take the limit of a dummy variable as it approaches infinity, and we integrate from 0 to b, and we have e to the minus 2t on tau integrated over time. So now if we evaluate this integral, we're going to get epsilon squared on r by the limit as b approaches infinity, and we have minus tau on 2 by e to the minus 2t on tau, evaluated from 0 to b. And recall the time constant is the resistance by the equivalent capacitance. So therefore R will cancel, and what we get is epsilon squared by the equivalent capacitance on 2, and we're taking the limit as b approaches infinity, and then evaluating this expression at 0 and b, we have minus e to the minus 2b on tau, and then minus minus e to the 0, which is 1. So as b approaches infinity, this term goes to 0. So what we get is the total energy dissipated by the resistor is 1/2 by the equivalent capacitance by the square of the electromotive force, which is equal to the total energy stored in the capacitors from part B as expected.